Hello, and thank you so much for watching this third episode of the AI Red Team Academy course. My name is Jarno Baselier, and today we are going to talk about neural networks. We are still laying the groundwork of AI, and neural networks are a big part of it. And I really need you to understand the theory behind this and all the terminology. And it's a hard chapter, it's a lot to get your head around, so please bear with me because I will try to explain everything as clear as I can. And yes, we are going to talk about layers and neurons and tensors and loss and optimizers, so a lot of important things. And please try to understand them before progressing to the next chapters. Well, this is a YouTube video, so we have to deal with all the YouTube shenanigans as well. Please consider liking this video because that will help this specific video a lot. And even better, subscribe yourself to my channel if you haven't already, because that will help my channel progress. I know a lot of the videos I do post are in Dutch, but you can still follow them along with subtitles, so that's a possibility. And I think if you like this video, there will be a lot of videos on my channel that you also like, even if they're in Dutch. That being said, one more thing, and that's the subscription. Please consider visiting my Patreon page, because my patrons, I have to say, will get access to a lot of extras. They will get access to AI pen test workshops. They will get access to new AI videos that I don't put on YouTube. They will get access to scripts, to slides, to other deep dives. So yes, please consider becoming a patron because it helps you a lot as a pen tester, as an AI pen tester, but it will help me a lot as well because, as you can imagine, creating these courses simply take a lot of time. So please consider becoming a patron. And now with that out of the way, it's time to start with this third chapter. Let's take a look at neural networks. So let's talk about neural networks. And in this specific chapter, we will talk about the basics and a little bit beyond the basics, because we will talk about the complete internal workings of a neural network, how it works, all the terminology, and the things you need to remember for future lessons. So these are the things that we are actually going to talk about. What is a neural network? Neural network as a function, neural network, the learning explained, at least the basics. We talk about neurons, tensors, layers, activation functions, loss functions, optimizers, overfitting, full learning loop, so the full learning loop and an analogy to make sure that all the things fall into its own place, that all the pieces of the puzzle fall into each other. And we have a transition to transformers. So what is a neural network? A neural network is a mathematical function that learns patterns from data. It is inspired by the brain, but to be honest, it is much simpler. It processes numbers, so it does not process any meaning or understanding. It works fully with numbers, and it learns by adjusting internal values, and we call those values the weights, and we will talk about weights in a few slides. So the key idea in a neural network is that it does not think, it simply recognizes patterns. As an analogy here, it is like teaching a child to recognize cats. So we show the child some examples of cats. Maybe the child makes some mistakes, but along the way, and the more we repeat it, the child will absolutely recognize cats in the future. So we will learn the child how to recognize cats. A neural network is one of the main methods used inside machine learning to learn patterns from data. Learning within a neural network consists of a few things which we will discuss. Well, a lot of these things we mentioned before: weights, loss, biases, etc. We can also describe a neural network as a function where the output is equal to what we put into it and all the parameters that process the input. As input, we can put in data like images, text, or numbers. We will have some parameters like weights and biases. And then finally, it will output something, and that something is its prediction. That is the thing that comes closest to what at least the model thinks, the thing that you ask. So as an example, we have a price. And in this function, there are a few variables like the size, bedrooms, and location. This is our input. So we will, for example, if we were to rent a room and we want to specify a specific size of the room, a specific location, the number of bedrooms, etc. And then we have some variable parameters, and all of these together will give me some kind of output of all the rooms that I can choose in and all the prices that belongs to these rooms. So let's say as input, we give it that I want at least a size of 120 square yards. I want 3 bedrooms, and the location I want is Amsterdam. And now with this input, we will weight this input with some parameters, the weights and the biases the model learned. So we do have some weights. We have a weight for the size, a weight for the bedroom, and a weight for the location. And a default bias or a default setting is that you'll need at least 50,000 euros. This is the base price and this is the bias. So even if we don't input anything, we will still weight the bias, so it still holds some value in the calculation. And in this example, the weight size is like 3,000 euros per square yards. We have 15,000 euros per bedroom, and for the location it is 200,000 euros for the location of Amsterdam. And all of this together will predict the output. So we will weight the price 120 multiplied by 3,000 plus 3 times 15,000 plus 200,000, and then the bias 50,000, and together we will get a end price of 655,000 euros. Keep in mind, as a red teamer, change one of the weights to minus 100,000 and label it discount. If you can do this, then the model will predict negative prices for large houses. Slip this modified parameter file into a shared model repository. Downstream apps trust the output and crash pricing systems. That is something that might happen. The complete process of learning, at least the basics of it, of training a neural network, is basically the estimation of the maximum likelihood. So the maximum likelihood or the most probable output. Let's say we have a button machine. Imagine a machine that outputs a 0 or a 1 each time that you press a button. Then the probability of outputting a 1 is in the formula the value p, and the probability of outputting a 0 is a 1 minus p. So if you press the button 8 times and you get this specific sequence 1 0 0 0 0 0 1 0, then we want to find the p, the probability of outputting a 1. And to do that, we will define the likelihood. And the likelihood is p for each 1 time. And this tells you how likely this exact sequence is. Well, if we do it with this specific sequence, the likelihood of getting the number 1 or the value p is 2 in 8 times. So we will probably get 6 zeros and 2 ones if we push the button 8 times. But now we only ran it through one simple sequence. To get a better likelihood number, we need to do this sequence of 8 pushes on the button, maybe 100 times. And then we will estimate the likelihood. Then that specific likelihood will be much more exact than the likelihood when we press the button 8 times just once, one sequence. So the maximum likelihood estimation, or the MLE, to find the value of p that maximizes the likelihood, you take a log likelihood, which is much easier to differentiate. You take its derivative with respect to p, you set it equal to 0 and you solve for p, and this results in a pretty complicated formula. The maximum, for example, in this first sequence we had 2 ones and out of 8 pushes of the button, which is a likelihood of 0.25. Now if we have another 8 inputs, or maybe these are 9 inputs, that's correct. And here we have 5 out of 9, which is a likelihood of 0.55. So far the machine produced outputs, but we didn't give it any variable input. The input was always the same. It was simply the push of the button. And this we call a unconditional distribution, but an LLM or a large language model works differently. LLMs are input conditioned machines. When you query an LLM, the model doesn't have one fixed probability P. Instead, it forms a conditional distribution. Let's say if we give it the input who is POTUS, then this might be the formula behind it. Asking who is POTUS gives one distribution. Asking who is the CEO of Apple gives another. In other words, the output probabilities depend on the input text. Now, how LLM or large language model training is exactly the same as estimating P. Suppose the training dataset contains the following variables after the sentence who is POTUS. We have Trump twice and Obama once. So then the model starts estimating with this specific formula, and we see the value Trump 2 out of 3 times and the value Obama 1 out of 3 times. And this is the same idea as estimating from 0-1 data, just on a much bigger vocabulary. The model assigns probabilities to all possible next tokens. A token is the basic unit the model predicts, like words, subwords, characters, punctuations, and then training is pretty simple. But it does this at a very large scale. So keep that in mind. For now, this was the basic idea. Now we start talking about neurons, because a neuron is the basic building block inside a neural network. It works like a tiny calculator. We have inputs, parameters, and outputs. And the input is that it receives numbers, which is probably data. For example, pixel values from an image or words turned into numbers. Then this input passes through specific parameters. It multiplies each input by a weight. It adds a bias. Then it applies a simple rule, activation of, we call this an activation function. And an activation function is a small mathematical rule inside every neuron. It decides whether the neuron should fire or send a strong signal, or if the neurons should stay quiet. And then the output is that it sends one number forwards to the next layer. So we have layers of data, and there are in those layers are neurons, and data passes through these neurons, and based on the parameters within these neurons, it fires the neuron or not, and this way it gives the data through or forward to the next layer, which does exactly the same thing. Now, as an example, a neuron that detects cat ears in a photo. If we give it an input with an image where the brightness of 100 pixels around the top of the head has a specific settings, it passes some weights, which it learned during training, high weight on ear-shaped pixels, for instance, and the output is a number between 0 and 1, where 0 stands for no ears and 1 stands for clear ears. So for 1, if it is 1 or nearly 1, it will send a strong signal or it will fire the neuron. For the neuron itself, we have the weighted sum, we have the activation, and finally we have the output, where the output is basically the same as the activation method, where the weighted sum is multiplied by input and biases. So we have a lot of input here. For example, we have different inputs. Then we have a weighted sum, a activation method, which in the end gives me the output. We will see this later on again much more clearly. What is a tensor? This is something different than a neuron, because a tensor is a multidimensional array used to store data. Because we pass data through the network through different layers, and this data got to have a specific form. And a tensor is the thing that we use to store the specific data. Those are basically arrays of numbers inside a network. It is a supercharged matrix that can have any number of dimensions. Essentially, a tensor is a data unit in use flowing through the neural network. We have 0D to 4D tensors. As a 0D tensor, which has no dimensions at all, we call this one a scalar. And this is just one number, like for instance the temperature, which in this example is 21 degrees Celsius. And this will look in the code like 21. We can have a one-dimensional tensor, which we call a vector. And this can be a list of numbers, in this example 5, divided by a comma. A 2D tensor, we call this a matrix with a horizontal and a vertical line. And this can be a black and white photo in a matrix of 28 by 28 pixels. Then we will have a 3D tensor called a 3D tensor. Well, that's easy. For instance, this is a colored photo where, like a black and white photo, we have a height and a width, but a color photo also has 3 different RGB channels. And this one is the third dimension. So a height, a width, and the RGB channels. And then finally, the 4D tensor, we call this a batch. And we can have 32 photos at once with a height, a width, and RGB channels. And this is not one photo, this is a batch of photos, so multiple photos. So including the batch makes a 4D tensor. And here we see graphically how this will look, and we can build this up until a 6D tensor, which is basically a cube with all layers of data. Depending on the action and position in the network, different tensors will be used. The input tensor can be anything like a batch, a sequence length, a embedding dimension. Then we have the weights or the tensors, the parameters, which are tensors by themselves, layers, in dimensions, out dimensions. And we have activation tensors, which flow through the layers. And finally, we have the output tensor, which is data that we get returned. And this can be a batch, this can be a vocabulary size, this can be anything, but all of these things hold different pieces of data, and so they work with different pieces of tensors. The calculation of the tensors happen by the GPU if a GPU is available. If not, it will happen by the CPU, but it is pretty resource intensive. As an example, we have an input image here. So we have 1 times a 28 by 28 tensor. This is a grayscale photo. We have the weight matrix. And the weight matrix is 512 multiplied by the format of the image is a total of 408 parameters. 401,408 parameters. We have a hidden activation function, which is 1 times 512, 1 times a 512 tensor. And for the output, we have a 1 by 10 tensor, and this gives the digit probabilities. Well, at least know that tensors are blocks that hold data, and these blocks can have different forms. Like I told you, a neural network exists out of multiple layers, and each layer contains neurons. We have the input layer, which is where the data comes in. So raw data enters as a tensor. For an example, an application takes a photo. In this case, 224 by 224 by 3. And this is a photo of a receipt. Then it goes to hidden layers. This is basically the brain. This is where all the data is processed and weighted. And there can be a lot of hidden layers. We don't know. We simply call it hidden layers. But there may be 3 hidden layers, and there may be 300 hidden layers. And those are convolutional layers, or conv. And these are to detect the edges, the corners, the textures on the photo. And this can be used to spot, for instance, a laptop within a photo. And then we have dense layers, which combine patterns into meaning. Like a train travel app learns that rain on a Friday might be the same as a 12-minute delay. And when data traveled from the input layer over the hidden layers to the final layer, which is the output layer, we have a final prediction. We have regression and a classification. A regression is the number, like for instance a price or the delay in minutes. The classification is a choice, like a cat or a dog, spam or ham. For example, web, you will love this Philip Hue lamp. And this is something that the internet might present you as something that you will love based on your previous search actions, etc. So the data that they have on you, this will be analyzed maybe in a neural network, and a Philips Hue lamp might be something you are highly interested in. And here we have the same thing again in a schema. And here as well, which is a little bit more clear, the first layer is the input layer where we have multiple kinds of data that we can input here. Then we reach the first layer with 8 neurons, the second hidden layer with 8 neurons, and the final hidden layer with 5 neurons. And in the end, we will have the output layer, and everything. Here we see the neurons that are colored, and so some of the neurons will fire, some of them will not. And in the end, we will get something like this. And where the zero line crosses the zero line, or the data and the weight values cross each other, is the most probable thing or the most probable output. And this will be the answer that will be given to the user. Well, why depth matters, or why more hidden layers matters. More layers means a deeper understanding of the data. One layer might see a simple pixel. 5 layers might see objects. But if you have more than 30 layers, it might understand sentences. So yes, the deeper or the more layers, the more we can learn the model. Then let's talk a little bit about the activation function, something we discussed before. Well, because what is it? Why is it there? If there wouldn't be any activation function, a neural network would be just a simple linear equation, where the output is always equal to the input multiplied by the weight and the biases. No matter how many layers we will stack, the whole network stays one big linear equation, a straight line. But with activations, neural networks can learn non-linear relationships. These functions are there so each neuron can bend the line. Activation functions are the switches that turn a boring straight line into a brain that understands the real non-linear world. And these 3 that we have here are activation functions. There are more, but those are the most well-known functions, I guess. We have the sigmoid activation function, the 10H activation function, and the ReLU activation function. Sigmoid is good for probabilities. 10H is better than sigmoid, and ReLU is default in deep models. It is fast and it trains pretty well. Then a loss function, really important, is the red pen score. It tells the AI where you went wrong by this much. So this is where you went wrong, and you were wrong by this much. And if we can minimize the loss, or we can minimize the errors, then we can increase the accuracy. Loss is only calculated during training to improve the model. So loss is something we see during training and not while using the model itself. And the loss model defines the mean squared error, or this is a loss function. And this function is used with prediction and regression. We have cross entropy, where we can choose between options and classifications. And we have Ewer, which is a hybrid between the mean squared error, which we discussed in the first line, and the mean absolute error, which we didn't discuss. And it behaves like MSE when errors are small, and like MAE when errors are large. Something that we might see here is how loss drives learning. We have a forward pass. This is data coming into the model, and a probability will be computed. And while learning, we will compute the loss. So how much was the model wrong? And then we will travel back to the model to correct the mistakes that the model made. So we will update specific weights and then we will repeat this until the model does not make any mistakes again and the loss is almost zero. And this part, the backpropagation, here is what is described right here. So this is how learning actually happens. The network uses the backwards path to calculate which weight caused the most errors. The network adjusts the weights slightly to reduce the error, and this happens thousands to millions of times. The good news is that this is automatic. There is no human intervention needed. This works for networks with billions of parameters. It's the same algorithm that powers every modern AI like ChatGPT, Grok, etc. Backpropagation computes so-called gradients. Now, what is a gradient? A gradient measures how much the loss or the error changes when a weight changes. If adjusting a weight makes the loss go down, the model is improving. If adjusting a weight makes the loss go up, the model is getting worse. So the gradient tells us which direction and how strongly to update the weights. A gradient, you can see a gradient as the slope of the loss function. And then we have optimizers, and optimizers change how fast and smoothly learning happens, so how loss is corrected. Backpropagation says these weights need to change by so much, and then the optimizer decides how big this step should be, in which direction this step should be taken, maybe smooth the gradient out, and how to remember all of these past steps for future iterations. The universal update rule is this: the new weight is the same as the old weight minus the learning rate multiplied by the adjusted gradient. So every optimizer just changes how that adjusted gradient is calculated. For red teams, replace the function, the optimizer function AdamW with plain SGD, which has no momentum. And if you do this in a production model, then the training becomes like 10 times slower and unstable. One line in the configuration file turns a 2-hour training into a 20-hour nightmare. So if you have access to this config, this is something you might be able to do, or you might at least document that you are able to do this. Here we see a timeline of different optimizers. The most recent ones are AdamW and Lion. And AdamW is stable and great for vision and language. And Lion is double as fast in training. It consumes half the memory and it is perfect for huge models. Another term we might see later on is overfitting. And this is when the model learns the training data by heart, including noise and outliers. Instead of learning the general pattern, we call this overfitting. As an analogy, a student who memorizes 100 old exams word for word gets 100% on those specific exams, but fails on new exams completely. To avoid overfitting, we split data into different sets to learn the model. We usually split the data in a training set, a validation set, and a test set, where the training set is the set where the model is trained on. So this is the set used to learn the patterns. The validation set, which is used to tune the hyperparameters. And then finally, the test set is the final unbiased performance check. Terminology, well, if you talk about terminology, we have data points, and a data point is a single training example. For instance, one photo of a receipt plus the correct amount, in this example 25 euros. Maybe a Dutch sentence plus the English translation. A cat image plus the label cat. Those are data points, but we also have epochs, and an epoch is one full lap through the entire data set. So if you have 60,000 images and you run one epoch, then the model has seen all these 60,000 images just once. If you run the learning curve 20 epochs, then the model has seen every image in the 60,000 image set 20 times. So it runs through this set 20 times 20 epochs. Now, why does overfitting occur? This occurs when the model has too many parameters versus their data points. It is trained too many cycles, too many epochs. There is no regulation, so no penalty for complexity, or maybe when there are dirty labels in play, which are human errors in the data set. You can spot overfitting when there is a very high accuracy on the specific training data, but a much lower accuracy on the validation data. So in the same analogy as we have seen, if the student remembers every question one by one, from the training data, it can answer this pretty good. So this will have a very high accuracy, but any new question is more hard to guess. So the quality of this output will be much lower on new questions. So the validation data. To fix overfitting, we can use more data. We can make use of dropouts, data augmentation, and early stopping. So early stopping or dropout, this is how we do it in the code, where the callback gets a early stopping with a patience of 10. We can use regulation. We can use data augmentation. Here are all examples on how we would program this in Python, but keep in mind that simply giving it more relevant data always wins and will help you fix your overfitting. The technique to prevent overfittings are called regulations. And we see the same thing back in this diagram. So if we take everything that we have learned and we put it all together, then we get basically a full training loop where each loop is equal to one tiny improvement. And this cycle, this learning cycle, repeats millions of times until the model is perfect or nearly perfect. And basically we have all of these steps. First off, we will input data in batches. For instance, 32 received photos. Then the forward pass happens. So the model guesses all the amounts, and after that's done, there will be a loss calculation where the loss function tells the model you were wrong by so much, and then backpropagation happens. So then that these can be a lot of weights, but in this case we have 127 weights. The loss function tells the model which weights caused most of the error. And then there's an optimizer function that adjusts those weights by a tiny bit. And this is repeated time and time again until the model is perfect. So when a model is, when we start learning and teaching a model, we can have, for instance, a batch size of 64, a dataset size with 120,000 examples, and we will let the model learn for 30 epochs. Then we will divide the dataset size in batches, so we will divide it in 64, and we have 30 epochs. So in total, the model learns by performing 65,250 different updates. And this is the same thing, but now in a schema. But maybe the most easy way of telling how a model learns is by using this analogy. So imagine if we want to teach a young child, and in this case, this is our neural network, what a dog is. Then we will start off with data or data points, and these are all the different photos or observations of animals we show to the child. Some of them are dogs, others are cats, cows, rabbits, etc. This is our raw input for the model. And then we have the input layer. This is where the data comes in. This is how the child receives the information. Each neuron in this layer is a sensor that picks up a specific feature from a photo. For example, is it furry? Does it have pointy ears? Does it have a tail? Etc. And then it travels, the data travels to many hidden layers. The child processes these features in different steps, the layers. The first layer might recognize some basic features. The next layer combines these basic features into a more complex pattern. For instance, that's a snout, those are paws, and so on until it reaches the final conclusion. Neurons in this case, these are all the small brain cells in each layer of the child's brain. Each neuron responds to a specific detail or pattern. and the weights, and this is how important the child considers a particular feature. If the child learns what a waging tail is, that a waging tail is a strong indicator of a dog, that waging tail feature gets a high weight, so that neuron will fire. Whiskers might get a low weight for a dog, but a high weight for a cat. We have biases, and these are the thresholds that the child needs to cross to believe a feature is present. Perhaps an animal needs to be very clearly furry before the child labels it as furry, or a bias that most animals it sees are dogs. Then we have the activations, and this is the thought process of each neuron. If a neuron receives enough positive input due to the weights and biases, it activates or it fires and passes the signal to the next layer. It's the intensity of a neuron's response. The output layer, and this is the child's final conclusion. For example, this is 59% surely a dog, or this is 70% likely a cat. Then we have the loss, and imagine that the child says, well, this is a cat, but it was actually a dog. The loss is how big the mistake was. The bigger the mistake, the higher the loss. And this is how we measure how good the child currently is at recognizing dogs. Then we have backpropagation, and when the child makes the mistake, a high loss, an adult tells them, no, that wasn't a cat, that was a dog. The child then thinks back through their thought process from the output layer all the way back to the input layer and slightly adjusts the weights and the biases. Maybe I should consider the tail more important than the whiskers when recognizing dogs. And this is the learning process, and this is what's happening at backpropagation. We have the optimizers, and this is how the child learns smartly. Instead of randomly adjusting weights, the child uses a strategy to reduce the loss as quickly as possible. It is like a teacher teaching the child efficient learning methods to make better decisions faster. The epochs, and each time that the child has received all the animal photos, we show them and learn from the feedback a complete learning cycle. That's one epoch, and the more epochs, the more the child has practiced. Tensors. Well, tensors are simply how all the data, the photos, the weights, the biases is organized and stored in the brain. They are multidimensional arrays. Think of a complex spreadsheet or a stack of spreadsheets that contain all the information the child needs to learn and predict. And finally, overfitting. Imagine the child has only seen pictures of golden retrievers. If they then see a German Shepherd, they might not recognize it as a dog because they have learned to specifically about one type of dog. They've learned the noise in the training data, the specific characteristics of golden retrievers too much instead of the general characteristics of a dog. And that's it for this specific module. This was an important module that makes us understand what neurons, layers, activations, loss, and optimization are, and how the training loop basically works with backpropagation, etc. In the next module, we will move to how transformers replace recurrence with attention, enabling LLMs. Another interesting theoretical topic that is pretty important for us to understand how AI and neural networks really work. But for now, you have the basic idea, and you already made a big step in understanding AI and neural networks, of course. Well, that was it for this specific course. I thank you so much for sticking with me, for trying to understand all the theory, and for following along. Thank you, and I hope that you did enjoy this video, and if you did, please like this video and subscribe yourself to my channel. And if you want to become a better AI pen tester, if you want to learn even more than I teach you in the YouTube course, which is already a lot, but all the nitty-gritties, all the details, the slides, the scripts, and all the extras, those will be only for my Patreon. So if you want those, please consider becoming a patron. And by becoming a patron, you'll also help me with my work, with my channel, with my courses. You will make everything simply better because you support the work that I do. Thank you so much for considering. I hope that you have an amazing day, and I hope to see you in the next course as well. Have a great one. Enjoy. Till next time. Bye bye.